first, let's look at data that is not considered big data. We'll do that using classifiers and data that can be separated by lines and planes. So what do we mean by big data? Well, the term big data refers to data sets that are both large and complex. So what does it mean to be complex? Well, for right now, a working definition, complex means there is a high dimensional underlying structure to the data. And it should be noted that often in data mining, we're as interested in the underlying structure as we are in the results produced by the algorithms themselves. So for example, here is a data set that is very large. There are 1,000,000 rows or 1,000,000 features that we're considering, but it's not complex. In fact, if you look closely, you'll notice that this data set is geometric features of squares whose sides range from a length of 1 to 1,000,000. Now, small data sets can't be complex. Large data sets aren't necessarily complex. So, to illustrate what it means to be complex, we're going to look at classification problems on different types of data sets. So classifiers are algorithms or problems in which the data set is divided into two classes, class 1 or class 0, and the goal is to predict the class of an unlabeled data point. Now, an algorithm which can predict the class is often called a classifier, and the data set, the part that's used to actually make the predictions, is sometimes called the features of the classes, and this is what we'll use. For example, let's look at a classifier where we have very large data, but the data is not complex. So our machine learning problem is, given the geometric features of a regular polygon, predict if the polygon is a triangle, which we'll call class 1, or not a triangle, which we'll call class 0. Here's the data. Notice that we have things that are class 0 and things that are class 1. It's pretty easy to see which ones are the triangles. They're the ones with 3 vertices. So for instance, if we're given this set of features and not told what class it's in, it's pretty easy to see that from the fact that it has 3 vertices and 3 edges, it has to be class 1. It must be a triangle. On the other hand, if we were given this data set and told there were 7 vertices, it's easy to predict this is class 0, not a triangle. Now let's look at this geometrically. So let's suppose we had a data set with only 2 or 3 numerical features. We can visualize those as points, and we can label the points with the class number. So all the green zeros are in class 0, all the black 1s are in class 1, and the red dot is an unlabeled point. And we'd like to ask the question, which class is that point in? Now let's start out with a very simple example. If there's a classifier problem, and if we can separate the data using a straight line so that class 1 is on one side and class 0 is on the other, then we'll say that this data is linearly separable. And so here we have an example of 2 data sets that are linearly separable. So how would we predict the class of an unlabeled feature point? So suppose we have this point here, and we'd like to know what class it's in. Just looking at it, you say, well, it's probably in class 1. It's close to all the 1s. If we draw a straight line separating the 2 sets, then that straight line says that the red dot is on the side where the 1s are. And so in that sense, we would say that we would classify the red dot as being in class 1. That's not the only method, however. Another method we might use to predict what class the red dot is in is we notice that it's very close to something that is colored black. In particular, we can look at all of the points and find that the point that's currently unlabeled is closest to a black. And so therefore, because its nearest neighbor is a 1, then we would predict this is also in class 1. A nearest neighbor classifier. Now we only want to consider linearly separable data. There are occasions when some data sets are clearly separable, but not linearly. And so we notice that this data set can be separated, but not by a straight line. So to get the linear separation, we can notice the scaling for the x and the y are ordinary scaling. But we could log transform and notice now that we're in log-log space, then we can separate the two data sets by a straight line. So even though it may seem obvious that the two classes are separated, we still only want to separate with straight lines. We don't ever want to use anything other than straight lines or their analogs, planes or hyperplanes, because we don't want to allow arbitrary curves of any kind. We do so because arbitrary curves can produce arbitrary predictions. So for example, let's suppose we simply draw an arbitrary curve that places all of the zeros inside of one region and all of the ones outside of that region. So here you can see me drawing, and I'm making sure that the ones are always on the outside of this curve. And if I close this curve, now notice that we've classified everything as either ones or zeros. Now I can do this again. So I'm just going to simply start at the same place, and I'm going to draw another curve. And again, my goal here is that I want the ones to be outside of the final region, and I want the zeros to be inside. So I draw so that the ones are always to one side of the curve and the zeros to the other. And once again, here I have all the zeros in one region. Now, let's suppose we have a point out in the middle of space. With our original classifier, we would say that it is a 1. But with the second one, we would say that it is a 0. Using an arbitrary curve, you can't really predict with any certainty what the true class of a point is, because the curve that you used to separate the two classes was arbitrary. So what can we do instead? Well, we can use dimensionality. Data that can't be separated in 2 dimensions may be separable in 3 dimensions. For example, here we have a data set, X, Y, and Z. It's in 2 classes. And let's just look at first the X and the Y. We want to look at this data set in 3 dimensions. To do that, we simply are going to rotate so that we can see all 3 dimensions, not just the X and the Y, but the X, the Y, and the Z. And now it seems pretty obvious, using either a separating hyperplane or a nearest neighbor algorithm, that that red dot should be classified as a 1. Now here's a real-world example. In 1936, Sir Ronald Fisher introduced the IRIS dataset. This is 50 samples in each of 3 classes. These are 3 different species of iris. He considered 4 features: the sepal length, sepal width, petal length, and petal width. Here's the first two rows of that data. The image over there shows you what a sepal and a petal are for an iris. So what we're doing is we're only going to have two classes. Class 0 means that it is in the eye setosa. Class 1 means that it is not in eye setosa. Using just the petal length and the sepal length, you can see pretty easily that we can separate eye setosa from the other two types of iris. If we look at just the sepal length and sepal width, it's not so easy. If we try to draw a straight line, it would be very hard. In fact, it's impossible to draw the straight line so that this eye setosa is in with its neighbors over here. But again, we're only looking at two factors. If we add one of the petal factors back in, if you use sepal width, sepal length, and petal length, clearly you can separate the two data sets. It's well known that the first type, the eye setosa, can be linearly separated from the other two, but the other two cannot be linearly separated from each other. So now we have all three classes of irises. Class 0 is the eye setosa, and class 1 and class 2 are two other species. The petal length and sepal length separate eye setosa from the other two, but the other two are not separated. So what happens if we rotate into one of the other factors? So let's put the petal width and petal length and sepal length all together. That gives us points in three-dimensional space, but we still can't separate the other two classes, the non-eye setosa classes, from each other. There still is no separating plane or hyperplane that we can use. So we've been looking at data sets that are not complex. The last data set being the exception, because classes 1 and 2 were the exception to the things that we had looked at before. So in summary, if classifier data set is linearly separable, it's not complex. If it can be transformed into a linearly separable data set, then it's also not complex. If the classifier data is not linearly separable for some of the features, but it is separable for all of the features, then it is not complex. However, big data is not only large, it is also complex.